So let's firstly start with a uniaxial crystal which has the property epsilon 1 equal to epsilon 3, and if it is not equal to epsilon 3, I will assume epsilon 3 is larger than epsilon 2. Such a thing is called a positive, and quartz is an example of such a crystal. Now, the index ellipsoid is d1 squared plus d2 squared by epsilon 1 plus d3 squared by epsilon 3 equal to 1. Let k vector be along epsilon 1. Then D is in the epsilon 2, epsilon 3 plane. Let us draw the index ellipsoid. This is my epsilon 3 and that's my epsilon 2. This distance is my root epsilon 3 and that is root epsilon 2. This thing is called the extraordinary refractive index, and that's called the ordinary refractive index. We will see why. Now, if D has to be in this plane, if D were in this direction, then E, which will be perpendicular to the tangent of the index ellipsoid at the point where they meet, will be in a direction which is different from D. That means DE will be in the E2, E3 plane. But we know DE must be coplanar with the direction K, which is epsilon 1. So this D is not allowed. The only D's that are allowed are if D is along epsilon 2 or D is along epsilon 3. So if D is along epsilon 2, I write D equal to D epsilon 2 cap. And the dielectric constant there is epsilon 2. So if D is along epsilon 2, then the Vp prime, which is what I call the prime, will be equal to C by NO. On the other hand, if D is along epsilon 3, then we will have epsilon 3 as the direction, which I will call Vp double prime equal to C by NE. Notice, if I write this as a vector, I will write that as K2 vector, and this as a vector, it is K2 vector. For the vector along, K1. For a vector which is along K1, there are two possibilities. One which is along epsilon 3, another which is along epsilon 2. The one who D vector along epsilon 2 will have a velocity given by C by N0, which I will call V ordinary velocity. Whereas if it were D were along epsilon 3, that will be called VE extraordinary velocity. So this is the analysis if vector was in the K epsilon 1 plane. Notice there is an axial symmetry rotating about when I rotate about x3 axis, because epsilon 1 is equal to epsilon 2. So if I take K vector equal to K epsilon 2, I will get a very similar analysis. So if I were along epsilon 2, then d with epsilon 1 will have ordinary velocity, d with epsilon 3 will again have extraordinary velocity. So much for this. Now let me take k to be along epsilon 3. If k is along epsilon 3, then d must be in the epsilon 1, epsilon 2 plane. And if I plot the index ellipsoid in that plane, that is a perfect circle. Now, any d will be allowed. If I take a d in this direction, the tangent to it is normal to d, and E will be along the same direction as d, so any d is acceptable. All of them will have the same velocity, all travel with VO, because this length is epsilon 1 or epsilon 2, same as that, and root epsilon 1 is related to VO, which is equal to C by NO. We will say all this in a slightly different way, and that is done by using surface, normal surface. This is done by moving k around various planes. So let's start with epsilon 1, epsilon 2. Suppose k is along epsilon 1, d must be along epsilon 2 or epsilon 3. If it's along epsilon 2, the velocity will be VO. Notice for our case, VO is greater than VE. And if it's along epsilon 3, it will be VE. And as I move out here, there is axial symmetry, so this will be the curve. These are the two surfaces. That means any wave moving along k, which is changing this way, this will be the surface of the wave, and this will be the surface of the wave. If k were doing in this direction, the wave would be like that. Now let's do the same thing in epsilon 1, epsilon 3, epsilon 3, epsilon 1. If it were along epsilon 1, then we have VO and then VE. And if we have here both epsilon 1, they will all be VO. So one will be like that, other one curve will be like that. Sorry, an ellipsoid like that. We will write the equation of this curve after this lecture. So this is the normal surface in epsilon 1 and epsilon 3. Epsilon 1 and epsilon 3 and epsilon 2 is very similar to this, because I just have to rotate it about this axis. If I rotate it about this axis, this normal surface, this will be some kind of a ellipsoid of revolution, and that will be, this is not quite an ellipsoid, we will write the equation for that. So that explains the normal surface.